Hello friends, welcome back to the Tetrahedral chemistry classes. So guys, in the last class I have explained the detailed molecular orbital diagram for the square planar complexes, and at last what I left with this tetrahedral complexes, right? So today I'll give you the little idea about the tetrahedral complexes molecular orbital diagram. Why I am saying the little idea, why not the complete description of these tetrahedral complexes through ligand field theory. The reason is that your tetrahedral complex, if you can recall the structure of your tetrahedral molecules, then this tetrahedral molecule is not having center of symmetry, right? When it is not having the center of symmetry and all bonds are equivalent, all four bonds are equivalent, right, which are connected to the central metal, right, they are actually identical, and due to this nature it is almost impossible, different orbitals cannot be made symmetrically distinct from one another, because these bonds are all equivalent in nature. So it is very difficult to actually give the clear picture about the ligand group orbitals of the tetrahedral complexes. So that's why this is the reason you will not find these tetrahedral complexes in pretty much detail in any of your textbook. Say if you are doing research on the coordination chemistry, especially on the tetrahedral complexes and the theoretical chemistry, right, only then you will have the idea about this, or you can go for the exclusively, see there are texts available in the form of the books, right, where exclusively they deal with the ligand field theory. Volumes are there, but I think for say CSIR, NET, GATE and various competitive examinations like your MSc entrance examination and even in the universities, right, you will not require the detailed tetrahedral molecular orbital diagram, right? For that means you will not require a detailed molecular orbital diagram of the tetrahedral complexes, because it is not possible actually. But what you can think, what you can remember, some things you can remember. Say these are the orbitals actually which can be used in making your sigma and the pi bond in the tetrahedral complexes. Say this is my s orbital, and this s orbital is having this term in the group theory, as I already told you in my previous lectures, that these terms are actually there, the origin of these terms are in the group theory. So this is A1, right, it is non-degenerate, right, and it's that's why 1 is written here. So this is the symbol used for this one, and whenever you s orbitals are involved, because they are symmetrically distributed among all the axes, so they always form the sigma bond. There is no problem in that, right? And if you go for your z orbitals, then dxy, dyz, dzx, they are actually in between the axis, right? Their orientation is in between the axis. It is a T2G set, but in that case we cannot say it is T2G, so the symbol will use the T2, right? And in my previous classes you have already seen, whenever dxz, dyz, dxy, these orbitals are there, they can form sigma bond as well as they can form the pi bond, right? This I have explained in the pretty much detail actually, right? And why I haven't written G here, as you know, the tetrahedral complexes, whenever you have the tetrahedral complex, these tetrahedral complex actually are not having the center of symmetry. That means when they are not having the center of symmetry, so you cannot put G here. G means G-rad, G-rad means presence of the center of symmetry, and at the start of the lecture I already told you there is no center of symmetry in the molecule, so G cannot be used here, so you will use this term T2 here, right? And this thing I have already explained in my crystal field theory, right? Lectures on the crystal field theory. And then after that you will have your p orbitals, px, py and pz, right? So these two orbitals actually have the same this d set as well as this p set, they have the same actually T2 symmetry. They are triply degenerate. T stands for the triply degenerate, right? And they have the same kind of the geometry. Why they have the same kind of the geometry, I can elaborate this particular point. See, whenever you have the tetrahedral complexes, right, so you will have either sp3 hybridization, okay, or you can have sd3 hybridization. So like your 3p orbitals, when overlap with the s, they form the sp3 hybridization to give the tetrahedral geometry. The same thing would be done by the d orbitals also. That's why they have given the same symmetry properties, right? So T2 term we will use for this d as well as the p, right? And then you left with this dx square minus y square and dz square orbital, and they are their lobes are oriented along the axis, right? Since they are oriented along the axis, okay, so there, and see these two have actually the degeneracy. So E means doubly degenerate, and again we will not use the G here because tetrahedral complexes is not having center of symmetry, right? So this will exclusively form your pi bond. So this thing you have to keep in mind, and you may have question in your competitive examination from this particular slide also, right? Now here see, as I already told you, explanation of the pi bonding in the complexes is quite difficult. So what I will do, I will explain the sigma bonding in the tetrahedral complexes, and this particular diagram I have taken from certain notes actually, right? They are available online, right? So I have taken that page from that particular book, okay? And moreover, see this sort of diagram you will find also in the coordination chemistry by Ajay Kumar, which is the actually Indian version of the Hui, okay? So how we can explain? You can see here these are the metal d orbitals, and when I'll talk about the metal d orbitals, so I have the 3D set, and this 3D, as in the previous slide you have seen, it has the two types of the set, E and the T2, and then you have 4s, that is A1, and 4p, that is T2, right? For timing you focus only on this one, okay? And since you can see your coordination number is 4 in that case, because we are dealing with the tetrahedral complexes, so we have the 4 ligands, okay? And when we have the 4 ligands, then ligand group orbitals should have or must have the same symmetry to overlap with these metal orbitals, right? This is the actually rule for your ligand field theory. So at the bottom you can see what I have written, ligand group orbitals for the ligand group orbitals, and these ligand group orbitals having this symmetry A1 as well as the T2, okay? Now what can happen, A1 and T2 according to their symmetry match, they can overlap here, resulting in the formation of the molecular and the bonding molecular orbital as well as the anti-bonding molecular orbitals, right? So first of all you can see this A, because it is cylindrically symmetrical, it forms a very strong sigma bond, so it is always lower in energy, and so this 4s, that is this A1, can interact with this A1. So you can see here, if I can highlight that, okay, so this is your A1, right, and which is actually matching with this one, and this is going in that direction. So this is where bonding A1, and definitely it must have the anti-bonding one, so this is star anti-bonding one. So this is the match for this particular one, okay? And then again you can see right, then you are having this T2 symmetry, right? Whenever you have that, see T2 symmetry is there in this d orbitals, so it can overlap here in that direction, okay? And T2 symmetry is also there in that case also, right? In the p orbitals T2 symmetry is also there, so this will also overlap here, okay, just like that. And then you will have a T2 anti-bonding, which is this one, T2 anti-bonding, which is coming through this particular interaction, and since you are having two T2 sets, so second T2 is also here in that case, okay? So this is how you can draw the molecular orbital diagram, and what you left with, you can see here, your E is not taking part in the any bonding interaction, so this will remain as non-bonding in this when you consider only the sigma bond, okay? Now, so this is the molecular orbital diagram. Now, if you say, if you have this particular complex, right, this complex if you are having, and you know in this particular complex your cobalt is in D7 oxidation state, because plus 2 is there, D7. D7 means it will have how many electrons? 7 electrons. So these d orbitals would have the 7 electrons. If I can put, so I will put the 7 electron here actually, okay, and 7 electron from here, and then 8 electrons from your these ligand group orbitals. So 8, 7, 15. We have to fill total 15 electrons here. So first of all, out of this 15 electron, you will see 8 electrons are there in the bonding intermolecular orbitals. You can see 1, 2, 3, 4, 5, 6, 7, 8, right? And then next 4 would be your in the non-bonding one. 1, 2, 3, 4, that is 12. Now you left with the 3 electrons. These 3 electrons actually are present in the triply degenerate T2 anti-bonding interaction. So some kind of anti-bonding interaction is also there, okay. And as you know, as this difference between E and T2 is as I have explained in the crystal field theory also, this is actually the tetrahedral crystal field splitting, which is the delta T. This is something very, very important. So I have written here bonding molecular orbitals, and since they are very close to the ligand group orbitals, so they have the characters of the ligands, right? And then you can see here these are the non-bonding, okay, and after non-bonding you can see these are the anti-bonding. So these anti-bonding, actually you can see this particular anti-bonding, right, this one, it is formed by the p and d mixing. That means d orbital and the p orbital will mix actually, and in that case the d orbitals are the contribution toward the for this mixing would be the contribution for d of d orbital would be greater than the p orbital when you have this first anti-bonding T2 kind of the interaction, okay. This is something important to note, that because this is very close to the d orbital, right? These molecular orbitals are close to the d orbitals, that's why the contribution of d is more. But if you come here actually at the top, T2 star, second type of the anti-bonding, which results with this interaction, right? So it will have the more character of the P. So PD mixing, earlier I have called this PD mixing or DP mixing, whatever, or here you can see PD mixing, but this time you can see this orbital is quite close to the P orbital of the metal, right? That's why the contribution in this contribution of P orbital in this mixing would be greater. This thing you have to keep in mind, okay. And this I have already explained, sp3 and sd3 type of the hybridization can occur in the complexes, right? So always use that T2 and 4p and 3d, right? In that case you can write in this way you can actually form the sigma, you can explain the sigma bonding in the tetrahedral complexes, right? So this is just the example of the D7. You can take some other examples also. Only this much you can explain in the tetrahedral complexes, and only this much would come in your examination if there, right? If something comes in the examination, then definitely it would not outside from this particular slide, okay. But the important point which I want to make here, this is actually the most generally, this is the most accepted energy level diagram for the tetrahedral complexes, in which your pi and the sigma bonding is actually explained. So this is the metal d orbitals which I have explained, though I haven't given their symmetry terms here. So this is the sigma bond, this is the pi bond, and in between you have your bonding, anti-bonding and the non-bonding molecular orbital, right? So what you can do, if you want, you can put their symmetries here, and just I did in the last slide, you can put the symmetry there, you can put the symmetry there, and then the symmetry here, and you can then correlate. So these are the bonding molecular orbital, all the sigma kind, and these are the anti-bonding, which is T2, E and T1 type, and then you are having the these are the pi bonding molecular orbitals, then these are the pi anti-bonding molecular orbitals of these kind, and these are the actually sigma and the pi anti-bonding molecular orbitals, right? And then you have this symmetry. So this is the most generally accepted diagram, which actually, see, if it is up to you whether you want to learn this particular diagram or not, but it is there in a book, and the name of the book is actually Chemical Bonding by O.P. Agrawal, right? It's a good book, right? It's a good book to understand the chemical bonding in the nature. So this is all about your tetrahedral complexes, right? So before signing out, I am requesting you kindly share the tetrahedron chemistry classes, right? and do share with your friends and hit the bell icon for the latest notification.